Okay, so now we are at the end of the talk, and we have now solved Jang's equation, and we would like to see if we cannot again deform this, see if we cannot prove a positive mass theorem anytime soon here. So what do we need to do in order to apply? So I mentioned before, we want to apply, we would hope at least to reduce down to the Riemannian setting where we could apply Shane and Yau's positive mass theorem result and assert that the mass is positive here too. However, we have to verify a few things for this to work out. And in particular, so we need first of all to show asymptotic flatness, meaning that the metric decays, the induced metric would decay to the Euclidean metric with two derivatives, as mentioned before, and we need scalar curvature integrability on the graph and so on, completeness. But we also we did have these cylindrical ends here. These things, we could have these blow ups and blow downs, and this was not mentioned in the setting of Shane and Yau. But let's see how things so let's simply try and check the first things. This can be circumvented, so of course these cylindrical ends, but for this talk we will simply say that we can do that, and we will not go into those technicalities here. Basically, to give a very short answer, it is that one can cap off these cylinders and be in control over the, so in the Riemannian setting there is a minimal surface proof. One assumed negative energy and constructed this minimal surface that couldn't exist because of other considerations, and that was the contradiction. But and one needs completeness, one needs and so on. And here we have this cylindrical ends that would perhaps destroy all of that for us. But one can do this, one can circumvent this in this setting too, and basically control that these minimal surfaces don't travel too far along these cylinders. But this we could leave for the Q&A session, for instance. So let's simply check first that the graph is asymptotically Euclidean. So if we had a sufficiently strong decay for the function, it is not so difficult to see that one would have then the induced graph. Again, the graph was G plus df tensor df. So if that metric decays sufficiently fast, then we would be asymptotically flat. And historically, Shane and Yau applied rescaling. That is to say, you take a point far out in the infinity and you invoke certain coordinates where you sort of zoom in, and then you say that the Yang equation is an elliptic equation, and you can do Schauder estimations, and in those coordinates you will then get control over the function and its derivatives. And then when you unscale, you basically get the decay rate needed for the graph to be asymptotically flat. In the hyperbolic setting, this does not work, and so one has to resort to other methods. And of course, when I describe these methods, they are the ideas of Anna Sakovic, who has proven the positive mass theorem for in the hyperboloidal setting now. In the spatial dimension 3, I will state more specifically the details of that result in a few slides, but bear with me for a moment. So the idea then instead is that one, I didn't mention this, but the lower barrier, if that had been a smooth function, then the metric of that would be asymptotically flat. That's an easy calculation to check, just like we checked with the exact solution that motivated this approach. And so what we do is that we replace the lower barrier by a what I call regularized barrier here. Namely, we assume it to be smooth and it has the same asymptotics. And as in this picture, we rewrite the Jang graph, and now we are again working close to the hyperbolic infinity. So we will write it as a graph over this lower barrier. We will write Jang's graph in terms of the barrier plus this hide function here. Now, and this is, one can do that. So there is one can do this in what is called Fermi coordinates or normal geodesic coordinates, which will exist around the lower barrier. And then the idea is then one can apply the same rescaling technique on that function. This is again also rather lengthy of a calculation and will be omitted. Currently, I would recommend the interested reader to have a look at the recently published paper by Anna Sakovic on the treatment of this problem in dimension 3. And again, we now have Wang's asymptotics again. So one can, if you recall, the Shane and Yao identity, where the scalar curvature was this expression in terms of there was one dominant energy condition, two square terms, and this divergence term. One can estimate those when working with Wang's asymptotics and show that, in fact, scalar curvature decays like this. In particular, it is integrable. So careful analysis again yields that the graph is asymptotically flat manifold with integrable scalar curvature. Although so far we have said nothing about non-negativity. But so just let me mention at this stage, and it's a nice little exercise if you want to calculate the hyperbolic energy as in the first mass vector component and the energy. So again, now because of this integrability of scalar curvature and asymptotic flatness, we can calculate the ADM energy is well defined in the infinity of the Yang graph. So we can talk about, we can calculate that and know it's well defined. Then in fact, we get this explicit expression. So in particular, we know that we're on the right track in proving a positive mass theorem, because now positivity of the first component here is tied to the positivity of the ADM mass. And we would like to have a non-negative scalar curvature, and this is again following Shane and Yao's ideas. This is one can conformally deform this into a scalar flat metric by. So again, we recall that under conformal deformations, if I have G hat, this induced metric on the graph, and I deform it by multiplication of some function, which I assume then to be positive and strictly positive and so on, sufficiently smooth and so on, and I call that metric G tilde, then the scalar curvature of G tilde metric is the following well-known expression. So we would like to solve for this here being 0 to get the scalar flat metric on the graph. And again, I am sweeping a bit under the rug that we have these cylindrical ends that require slightly further treatment. But briefly then, one can of course solve that equation. The function has asymptotics, is non-negative, is positive, strictly positive, and has asymptotics like this. And so in particular, again, we have not, we are still within the asymptotically flat regime and so on. So we can talk about the graph of the ADM energy of the graph after this conformal deformation, and A here satisfies this inequality. And one can show that the ADM energy under this conformal change changes like the following. And this is also a nice little exercise if you feel like it. And in total, if one now combines these estimates, we get that the metric that we now end up with on this scalar flat, asymptotically flat graph is bounded by the mass vector. So if we can show that this guy is non-negative, then the positive mass, positive energy theorem, really, in the hyperbolic positive energy theorem would follow. So, and I mentioned that we can circumvent the problem of cylindrical blowups, but I will not go into that here. And so Anna Sakovic proved for dimension 3 the following theorem, and let me now announce that this has been generalized to dimensions 4, 5, 6, and 7, that if M GK is complete asymptotically hyperboloidal initial data of L alpha tau tau 0, and we need 6 derivatives because we lose one for the density theorem and 2 for in the Fermi coordinate setup. And so if the dominant energy condition holds, then the mass vector, as we defined above, is future pointing causal. Energy is bounded below by the length of the momentum. And so we have not discussed rigidity so much, or the proof of it here. But furthermore, if M and GK has Wang's asymptotics, then the energy equaling 0 means we can embed our initial data isometrically into Minkowski space as a space-length graphical hypersurface with second fundamental form. Okay. And we speculate, of course, that the minimal k-slicings in the recent article by Shane and Yao, where the Riemannian positive energy theorem was proven for all dimensions, we speculate that this may be applied to solve Yang's equation in all dimensions, which would yield, I mean, it is not expected that this dimensional problem is anything but technical. So we speculate that those techniques may apply to solve it for all dimensions. And with that, I thank you for the attention. It's been a privilege to give this talk, and I look forward to questions and comments in the Q&A session. You're, of course, anyone with questions or comments are welcome to email me. And I realize now I have not included the email in the presentation, but this is easily found via a bit of Googling. And so thank you very much.